the nervous tissue all the way to these filaments sliding past one another. We need to make sure we know which neurotransmitter is involved, and it's pretty straightforward when it comes to skeletal muscle contraction because, as we said, we're always going to be dealing with acetylcholine. We need to realize that we are depolarizing the membrane of the muscle. We need to realize that in order to have this contraction cycle move forward, we need to make sure calcium is going to be available. And the reason that calcium is going to be available is due to that impulse that is coursing down over the membrane of the muscle. We need to know what makes up those individual filaments in the muscle, those thick filaments and those thin filaments, so that we know how they can slide past one another. I think it's great to be able to diagram this process from beginning to end. From beginning to end. Yes, yes, yes. Very good. So, if that was contraction, we should talk about almost the opposite, relaxation. And when it comes to relaxation, we're going to need to be able to break down our neurotransmitter. And the way that we break down our neurotransmitter of acetylcholine is with an enzyme, acetylcholinesterase, ACHE. This is going to break down the acetylcholine that we have within the synaptic cleft. When we don't have any acetylcholine that is going to remain, our action potentials are going to be inhibited. They're going to cease. If there are no action potentials, calcium isn't going to be released from the sarcoplasmic reticulum, and our calcium channels are going to close. When the calcium channels are closed, we're going to take the calcium that had left the sarcoplasmic reticulum, and we're going to bring it back. One might say we are going to sequester it into the sarcoplasmic reticulum. So we have the aptly named calsequestrin, which is the calcium-binding protein, which helps sequester the calcium into the sarcoplasmic reticulum. I'm sure you've all heard about sequestering a jury before. You can think about those jurors as those of atoms of calcium being brought into the sarcoplasmic reticulum. And this is a pretty powerful protein in so much it allows for a tremendously higher concentration of calcium in the sarcoplasmic reticulum than in the cytosol of the cell. Any questions on this at all? So it's just about the opposite of contraction.
So is all of this part going to be on the quiz too?
All of this is important, but if we had a quiz today, it would not be on the quiz today. But it's all important to know. So, troponin and trypomyosin, that complex is going to recover the binding site that we have on actin, and we are going to be able to be ready for the next contraction. We should probably mention a few things about rigor mortis as well. When it comes to rigor mortis, this deals with both contraction and relaxation. It's when our muscles are going to be stiff, when they are going to be rigid a few hours after death. Why? Well, after death, we know that we're not going to be producing any more ATP. And after death, calcium that we have that was in the sarcoplasmic reticulum is going to be leaking out from the sarcoplasmic reticulum. And when that calcium leaks out from the SR, we're going to allow that of our myosin head to bind to actin. So we can go through that part of the contraction cycle, but that's about it. Once again, individual's dead. No ATP is going to be produced. No ATP being produced, no cross bridge can be detached, which is why the muscles are going to be rigid. This lasts for about a day. After a day, however, as cells begin to obliterate, break down, some of our proteolytic enzymes digest the cells, start breaking apart, and the muscles aren't going to be as rigid. I've seen some profound cases of rigor mortis in the past. Back in the time when I used to work in the morgue, I would take a body down to the morgue on the cadaver cart, put it in the refrigerator, come back 8 hours later, and the cadaver is sitting up on the cadaver cart. By that I mean the following. We have contraction of the abdominal muscles. So we might be sitting up maybe 10, 15 degrees or so tops. Still, it's noticeable. There's a lot more contraction than when we put the body in the corner in the first place. Did I ever tell you the story of what I used to do to new nursing students? Maybe, did I tell you that last session? Did I with Rigor Mortis? Did I? Okay, good. Well, then I don't want to do that again. But I'm more than happy to share that with anyone in the future. If you forgot. Wally?
Where are the photolytic enzymes?
From the cells as they actually they break down. They're usually stored in structures like that of lysosomes, and when those lysosomes start degrading, those enzymes are released. We should mention a few things as well today about the length of muscle fibers. And when it comes to the length of muscle fibers, we can talk about the amount of overlap that's going to exist between the thick and thin filaments. Usually, when we're at rest, that amount of overlap is going to be somewhere between 70 to 130% of the optimum. And of course, we can have issues if we are going to go one way or the other from the number. We can stretch the muscle past the optimal length when we don't have as many cross bridges that are going to form, or we can overstretch the muscle as well, and we also don't have as many cross bridges that are going to be forming. It looks something like this. When we look at this length tension curve, we can look at the amount of tension that is going to be produced in the muscle depending upon that of the optimal length. So when we look at this optimal length that we have, this is when we're going to be able to produce the greatest amount of tension. But what happens when that muscle is going to be understretched, of course the amount of tension that's going to be able to produce is going to be diminished. When the amount of stretching increases so that the muscle is going to be overstretched, you can see as well that the amount of tension that's going to be produced is going to be much less than when we're in that optimum length of, as we said, somewhere between about 70 and 130%. We should mention a few things about the neuromuscular junction. We've already talked about this space that exists between the nerve cell and the muscle cell, and we have that synaptic cleft, that gap that exists between these different tissue types. What do we find here, though, at the neuromuscular junction? Well, we keep talking about that neurotransmitter that we use for communication, acetylcholine. When acetylcholine binds to acetylcholine receptors, there are numerous acetylcholine receptors on a typical skeletal muscle cell. And any one given motor end plate, we could be talking about somewhere in the magnitude of the tens of millions of receptors for acetylcholine. When we look in the synaptic end bulb, that terminal portion of the neuron, we can see the neurotransmitters that are going to be packaged within these synaptic vesicles. These synaptic vesicles fuse with the membrane of the neuron, and their content, the actual acetylcholine, gets released into the synaptic cleft, and we see acetylcholine binding to the acetylcholine receptor, causing the opening of the sodium channel, allowing the propagation of the action potential. I would make sure that you know this well. And once again, just for repetition, we've talked about how that impulse is going to be traveling down the neuron, down to that terminal portion of the neuron, which we call the synaptic end bulb, where we have our synaptic vesicles that are filled with acetylcholine. Acetylcholine is going to travel across the synaptic cleft to bind to those postsynaptic receptors on the muscle motor end plate. That's going to cause the opening of the sodium channels and the influx of sodium. Sodium, of course, is positively charged. So the inside of the muscle is now going to become more positively charged. And this is what causes that action potential to propagate all the way down to those T-tubules, which causes the sarcoplasmic reticulum to release calcium. Muscles can contract. As muscles contract, force is generated. And when it comes time for relaxation, we said that we need the enzyme ACAG, acetylcholinesterase. It's acetylcholinesterase that causes the breakdown of acetylcholine so that relaxation can ensue. We should probably also mention a few of the drugs that work at the neuromuscular junction. Oh, such as botulism. Ooh, the botulism toxin. Oh, what do we know about this? Well, it causes muscle contractions to simply cease.
Botox.
You wanted to ruin my thunder. Yes, I of course was going to say, can you believe that individuals will knowingly go and pay money to have this toxin shot into their face? Look at that botulism toxin. Botox. There you go. That is your Botox to try to smooth out some of those wrinkles. We have issues with this toxin, however, when it comes to causing the cessation of muscle contraction in regard to the diaphragm. Oh, that dome-shaped muscle that separates the thoracic from the abdominal cavity. If that muscle is no longer going to be able to contract, we're not going to be able to suck in much, if any, oxygen, and now we are no longer compatible with life. Question?
What about with the heart? Why is it just the diaphragm contract? Does it affect your other muscles then too, like your heart?
Any muscle can be paralyzed when it comes to botulism toxin. Yes. This is why when you go to a grocery store and they have the discounted cans for sale that have the blown out appearance, you should probably avoid those cans because those are the cans that might be thriving with this toxin. Home canners who have issues when it comes to the cleanliness of their home canning can have issues with botulism toxin as well. Question, Alex?
Can they fix that just by injecting calcium?
No. A situation like this, it's usually not going to be all that beneficial. But in theory, as far as what we just talked about, it would make sense with the physiology. There's other drugs like that of Curare that cause paralysis as well by blocking the acetylcholine receptor. If we block the acetylcholine receptor, it doesn't matter how much acetylcholine is going to be released. It simply cannot bind to the receptor because that receptor is blocked. And if acetylcholine can't bind to the receptor, there's no propagation of an action potential. No propagation of an action potential, no muscle contraction, which is why this is used when it comes to relaxing muscles during surgery. Back in the day as well, monks hundreds of years ago would also tip their arrows with Curare because when you shot your target, they are now incapacitated, and it's difficult for them to run away when their muscles are paralyzed. We could also mention that in neostigmine, this anticholinesterase agent. Look at the name. The name tells us what it's going to do. It is an anticholinesterase agent. So it's going to be blocking the removal of acetylcholine. So if we're blocking the removal of acetylcholine, that means more acetylcholine is going to be available. If more acetylcholine is available, we're going to have even stronger muscle contractions. When it comes to a condition like that of myasthenia gravis, where muscle contractions are weak, some patients can benefit from the administration of neostigmine. You can also use neostigmine when it comes to an antidote to counter the effects of Curair after surgery. We should also talk a little bit about muscle metabolism and where ATP is going to come from in order for this contraction cycle to continue. Before I do that, though, let me go back for a second and just check on my students to see if, by chance, any of them can hear anything. Let's see. Samantha Diaz, why does it take so long for some people to get rigor mortis than others? Samantha, simply because of differences in physiology from one individual to another. Does the age of a person when they die play a role in the time frame for rigor mortis? Usually not. Of course, though, at either extremes, it could be a factor. But good questions. Thank you. We were talking about sources of ATP. And we know muscles have ATP, but the amount of ATP that we have in the muscle only is going to be there for maybe a couple seconds tops. Who can help me out? If we only have a couple seconds of ATP in a muscle, what type of activities might last just a couple of seconds?
Sprint.
I heard the start of a sprint. Sure, the start of a sprint. A platform dive. Sure, things that might last only a couple of seconds. If we are, though, partaking in activities that last more than a couple of seconds, we need to be able to have other sources to produce ATP. Hence that of creatine phosphate and aerobic and anaerobic respiration. When it comes to creatine phosphate, this is going to allow us to generate ATP for maybe as much as 15 seconds of activity. For some of you, that might be a 100-meter dash. For Dr. Bruder, that might be a 50-meter dash. So, when it comes to creatine phosphate, we have our ATP with creatinine that are used to form creatine phosphate. When we are going to need energy for muscle contraction, we are going to cleave that of creatinine from that of our ATP, and we are left with ADP and that phosphate that we have broken out. But because we have removed that phosphate group, we've liberated that energy that's stored in the high energy bond. We can take that creatine phosphate and we can add that to the ADP. We are going to produce that to creatinine, and when it comes to muscle relaxation, we can take the ADP, break off that phosphate, and we have that of creatine phosphate and the ADP. So as we said, though, this is only going to give us maybe 15 seconds of ATP production tops. However, after 15 seconds, we need to turn to other sources for ATP production. Things like that of anaerobic cellular respiration, where we are going to drive this process not in the presence of oxygen, and we're going to be able to produce just that of a couple molecules of ATP. But this is going to give us somewhere between 30 and 40 seconds of activity for many people, a 200-meter race. What about, though, the big question is, when it comes to activities that last for more than 30 seconds? Well, then we're going to use aerobic cellular respiration. And when we are going to be breaking down glucose in the presence of oxygen, we're going to be producing 36 to 38 molecules of ATP for every molecule of glucose, just depending on how you do your math. Over time, though, muscle, of course, is going to fatigue, where we're not going to be able to contract the muscle anymore. Why? Well, it could be a protective mechanism to prevent the muscle from damaging itself. It could be that we've obliterated those creatine and phosphate stores, or that the amount of calcium within the sarcoplasm has been diminished. If we don't have enough oxygen, if we don't have enough glycogen, muscle can fatigue. When we have too much lactic acid buildup and production of ADP, we're going to have muscle fatigue as well. Question, Samita? Samita?
So the creatinine is causing
It is. Yes. Yes. Okay. With that being said, and me having a few audio issues, I'm going to end things here for my online students right now. However, I'm going to post this for my online students as soon as I can. There will be a little bit more that I will add to this later on. I'd like to thank the two of you for joining us live, and I hope that you will join us more in the future. So thank you very much, online students. My on-site students, however, time for a quiz.